Time is not the rigid river we perceive it to be. We are about to uncover 30 distinct theories that could make time travel a reality, from the well-tested principles of Einstein to the speculative edges of quantum physics. By the end of this journey, you will understand how the very fabric of the universe might be manipulated to journey through the ages. We will explore how cosmic strings could twist spacetime into loops and why some physicists believe every decision you make spawns a new universe. Which of these ideas do you believe could one day unlock the secrets of time? Einstein shattered the notion of a universal clock with his special theory of relativity. He revealed that time is not a constant river flowing at the same rate for everyone. Instead, it is a personal experience, a rhythm that changes depending on how fast you are moving. The closer you travel to the speed of light, the more your own time slows down relative to someone standing still. This is the bizarre reality of time dilation. Imagine a pair of twins. One remains on Earth while the other boards a spacecraft and journeys to a distant star at a velocity approaching light speed. For the traveling twin, the trip might feel like only a few years, but upon returning home, they would step out of their ship to find their Earth-bound sibling has aged decades. This is the famous twin paradox, a thought experiment that illustrates the real, physical warping of time. We are not just talking about theory. This effect is measured and corrected for every single day by the Global Positioning System, or GPS. The satellites in orbit are moving so quickly relative to the Earth's surface that their onboard clocks literally run slower, falling out of sync with ground-based timekeepers. If engineers did not account for this relativistic shift, your navigation would be off by several miles within just a few hours. This is not science fiction. It is proven physics. The very foundation for time travel is laid right here, in the understanding that time is not a rigid scaffold but a flexible fabric waiting to be stretched. But Einstein was not finished reshaping our reality. His next great leap, the theory of general relativity, revealed that gravity is not a simple force of attraction. Instead, it is the warping of the very fabric of the universe, the bending of spacetime itself by mass and energy. A massive object like our Sun creates a deep well in this cosmic fabric, and the planets orbit not because they are being pulled, but because they are following the curved contours of this warped spacetime. And just as motion can stretch time, so too can gravity slow its very heartbeat. The stronger the gravity, the slower time itself will pass. Picture two incredibly precise clocks perfectly synchronized. Place one at sea level where Earth's gravitational pull is strongest, and carry the other to the top of a tall mountain where the gravity is ever so slightly weaker. Leave them for a year. When you bring them back together, you would find a real, measurable difference. The clock that remained at sea level would have ticked just a little bit slower, lagging a tiny fraction of a second behind its mountaintop counterpart. This is not a thought experiment. It has been confirmed with astonishing accuracy. Scientists use atomic clocks to measure this effect, proving that time truly does run slower in a stronger gravitational field. This gravitational time dilation is the second key to understanding how we might one day build a time machine. If gravity can slow time, then what could an unimaginably powerful gravitational field accomplish? The crushing gravity near a black hole could theoretically stretch seconds into years, creating a natural time distortion of epic proportions. It is within these warped regions of spacetime that physicists speculate we might find or create closed timelike curves, paths that loop back on themselves, allowing for a journey not just into the future, but potentially into the past as well. The warping of spacetime by gravity suggests a truly mind-bending possibility. What if the fabric of the cosmos could be pinched together, creating a shortcut between two distant points? This is the theoretical foundation of the wormhole, a concept first proposed by Albert Einstein and Nathan Rosen. Often called an Einstein-Rosen bridge, a wormhole is imagined as a tunnel or a cosmic subway connecting two separate locations in the universe. If you could enter one mouth of this tunnel, you might emerge from the other an unimaginable distance away, having traveled a much shorter path through the warped fabric of reality. But the implications are even more profound than instantaneous travel across space. If one end of the wormhole were moved, or if it were subjected to intense gravitational forces, time itself could pass at different rates for the two mouths. A traveler stepping into the stationary end might find themselves exiting the moving end not just in another place, but in another time. The journey through the tunnel could become a one-way trip to the past or the future. Constructing such a bridge through time, however, requires a substance that defies our everyday experience. A naturally occurring wormhole, if one could even exist, would likely be incredibly unstable, collapsing into a pinpoint the moment anything tried to pass through. To keep it open and traversable, theoretical physicists suggest we would need a form of exotic matter. This is not merely an unknown element, but a substance with a truly bizarre property, negative energy density. Think of it as a kind of anti-gravity, a material that pushes spacetime apart rather than pulling it together. This exotic matter could theoretically line the throat of the wormhole, propping it open against the immense forces trying to crush it shut. While we have glimpsed effects resembling negative energy in certain quantum experiments, harvesting enough to stabilize a cosmic tunnel remains a fantasy far beyond our current grasp. Even if we solved the immense engineering challenge, a new and terrifying problem would emerge: the paradox. Imagine traveling back through a stable wormhole to a time before it was ever created. What would happen if you were to somehow prevent its construction? You would have erased the very method of your own journey, creating a logical inconsistency that seems to violate the core rules of cause and effect. This is the famous grandfather paradox, a staple of science fiction that poses a serious question for physicists. How can the universe allow for a sequence of events where the cause is erased by its own effect? Some researchers propose that the universe would simply not permit it. The laws of quantum mechanics might conspire to prevent any action that would create a paradox, perhaps through a series of improbable accidents that stop you from interfering with the past. Another, even more radical idea is that your journey would not change your own past, but would instead branch off into a new parallel timeline, a concept we will explore in much greater detail later. For now, the wormhole remains a tantalizing blueprint, a theoretical ticket to the ages that hangs on mysteries we are only beginning to understand. These cosmic threads are remnants of the universe's violent birth, theoretical scars left over from the Big Bang itself. Known as cosmic strings, these are not physical cords you could touch, but unimaginably dense, one-dimensional flaws woven into the very fabric of spacetime. They are thought to be thinner than a single atom, yet a single inch of one could contain the mass of an entire mountain range. This incredible density allows them to warp the space around them in ways that defy common sense, bending the path of light and twisting the flow of time into loops. If you were to travel in a precise path around one of these strings, you might find that your journey through space leads you back to your own past, creating a closed timelike curve. This is not a journey through a tunnel like a wormhole, but a circuit carved directly into the cosmos. The effect becomes truly possible for time travel when you bring a second cosmic string into the picture. Imagine two of these infinitely long, ultra-dense filaments flying past one another at a significant fraction of the speed of light. Their combined, swirling gravitational fields would twist spacetime into a knot so tight that the distinction between past and future could temporarily blur. A spacecraft following a very specific, slingshot-like trajectory around this dancing pair could, in theory, be flung not just across space but backwards through time. It would be like surfing a wave of warped reality, riding the contours of a gravitational maelstrom to arrive at a point before you ever left. Yet the challenges of such a journey are as vast as the cosmos itself. First, we have no direct evidence that cosmic strings even exist, though some cosmologists believe their faint gravitational imprint might be detectable in the cosmic microwave background, the afterglow of the Big Bang. Even if we found one, the energy required to manipulate it or to move two of them at near light speeds is beyond any technology we can conceive of today. It would require harnessing the power of stars or perhaps even entire galaxies. So while the mathematics of general relativity allows for this incredible possibility, turning cosmic strings into a practical time machine remains a dream on the furthest edge of theoretical physics. It is a reminder that the universe may have woven its own pathways through time, waiting in the darkness for a civilization advanced enough to follow them. A different kind of machine emerges not from cosmic strings, but from the sheer power of rotation. This is the Tipler cylinder, a thought experiment by physicist Frank Tipler that pushes the mathematics of general relativity to its absolute limit. Imagine an object of almost incomprehensible density, a cylinder longer than any star system, spinning at a significant fraction of the speed of light. According to Einstein's equations, such a massive, rotating object would not merely sit in space. It would actively grab the fabric of spacetime and drag it along for the ride, a phenomenon known as frame dragging. The faster it spins, the more it twists the universe around it, warping the coordinates of reality into a tight helix. If you were to pilot a spacecraft on a precise, spiraling path around this colossal, spinning cylinder, following the contours of this dragged spacetime, you could find yourself on a closed timelike curve. Your journey would loop back on itself, not just in space, but in time, potentially allowing you to arrive at a moment before you even began your voyage. It would be like canoeing down a river that suddenly twists into a perfect circle, bringing you back upstream. The obstacles to building such a device, however, are as fundamental as they are immense. The cylinder would need to be constructed from a material denser than a neutron star, where a single teaspoon of matter would weigh billions of tons. Even more prohibitive is its required length. For the time travel effect to work within the equations, the cylinder must be infinitely long. This immediately places the Tipler cylinder in the realm of pure mathematical theory, a fascinating proof that general relativity permits such bizarre possibilities, even if our universe provides no clear way to actually construct one. It stands as a monument to a powerful idea that rotation itself can be a force capable of bending time to its will. The ultimate time machine might already exist, forged in the collapse of a dying star. Rotating black holes, described by physicist Roy Kerr's equations, are not the simple, inescapable pits of darkness we often imagine. Their intense spin warps spacetime into a shape far more complex than that of a stationary black hole. At the very heart of a Kerr black hole lies not a crushing point of infinite density, but a ring-shaped singularity. This is not a solid object, but a whirlpool of warped physics, a gateway of pure energy spinning at nearly the speed of light. The theoretical implications are staggering. If you could somehow survive a journey through the event horizon, the point of no return, you might find a path through this ring. It would not be a tunnel of empty space, but a violent transition. Mathematical models suggest that passing through this ring singularity could spit you out into a completely different universe or deposit you at another point in time within our own cosmos. It would be the ultimate cosmic shortcut, a backdoor written into the fabric of reality by gravity itself. Yet this path is guarded by unimaginable perils. Just inside the event horizon of a rotating black hole lies a theoretical boundary called the inner horizon. This is a region of infinite energy, where light and radiation from the entire future of the universe are focused into a single searing wall. Any object approaching this cauldron would be bombarded with an infinite amount of energy, utterly vaporized in an instant. Even if you could somehow bypass this firewall, the tidal forces would be your next and final obstacle. The difference in gravity between your head and your feet would be so immense that you would be stretched into a long, thin stream of atoms, a process physicists call spaghettification. So while the mathematics of the Kerr metric paints a picture of a gateway to other worlds and other times, it is almost certainly a one-way trip to destruction. The black hole offers a key to the ages, but it is a key that melts in your hand the moment you try to turn it. A different path to the past does not require moving through space at all, but instead involves warping the space around you. Physicist Miguel Alcubierre proposed a theoretical engine that would achieve effective faster-than-light travel, not by pushing a ship through the cosmos, but by manipulating the fabric of spacetime itself. The Alcubierre warp drive would function like a cosmic surfboard, riding a wave of distorted reality. The ship itself would sit motionless inside a flat region of spacetime called a warp bubble. Meanwhile, the drive would contract the spacetime immediately in front of the bubble, pulling the destination closer, while simultaneously expanding the spacetime behind it, pushing the point of origin further away. The ship would be carried along by this moving hill of spacetime, never breaking the speed of light locally, yet arriving at its destination faster than a beam of light could travel the normal distance. It is a brilliant loophole in the cosmic speed limit. The implications for time travel emerge directly from the rules of relativity. If you can travel from Earth to a distant star faster than light from certain perspectives, your arrival could appear to happen before your departure. This is where the closed timelike curve re-enters the story. By carefully plotting a course with a warp drive, you could theoretically create a path through spacetime that loops back on itself, allowing you to return to your own past. You would not be turning the ship around, but rather steering the bubble of warped space on a trajectory that circles back through time. The obstacle, once again, is the fuel. To create and maintain this warp bubble, the Alcubierre drive requires a shell of exotic matter with negative energy density. This is not just a rare substance, it is a material that possesses less than zero energy, a concept that seems to defy logic. While quantum mechanics allows for fleeting instances of negative energy in what is known as the Casimir effect, the amount needed for a practical warp drive is astronomical, equivalent to converting the mass of entire planets or even stars into this bizarre form of energy. This has led to a fierce debate at the very frontier of physics. Some theorists argue that quantum mechanics fundamentally forbids the stable existence of such a warp bubble, that the laws of nature inherently protect causality and prevent paradoxes from forming. Others continue to refine the mathematics, searching for a configuration that might require less impossible fuel. The Alcubierre drive remains a breathtaking idea, a blueprint for a machine that controls the geometry of the universe. It teaches us that the ultimate vessel for time travel might not move through space, but instead bring time to you. While the immense gravity of black holes warps time on a cosmic scale, the answer to time travel's greatest paradox might lie in the ghostly world of the impossibly small. Quantum mechanics, the rules governing atoms and particles, presents a reality far stranger than any cosmic string or wormhole. Within this realm, a single particle can exist in multiple states at once, a phenomenon known as superposition. It is only when we observe it that the particle seems to choose a single reality. This bizarre behavior led physicist Hugh Everett to a radical conclusion in the 1950s. He proposed that the particle does not actually choose. Instead, every possible outcome of a quantum event does in fact occur, but each one plays out in a newly created parallel universe. This is the many worlds interpretation. Every flicker of chance, every decision made by every particle causes the cosmos to continuously branch, splitting into a near-infinite tapestry of alternate realities. In one universe, you might be reading this script. In another, you decided to watch a different video entirely. The implications for time travel are profound. Journeying to the past under this view would not be a return to your own history. You would be crossing into the past of a parallel universe, a timeline that branched away from your own at some point in its history. The moment you arrive, your very presence becomes a new quantum event. If you were to step back in time and prevent your grandfather from meeting your grandmother, you would not erase your own existence. You would simply be acting within a different timeline, one where you were never born. Your original universe with your original history would remain completely untouched. This offers an elegant escape from the inescapable logic of the grandfather paradox. The universe does not need to prevent you from changing the past because you are not changing your own past. You are merely a visitor, and your actions become the seed for a new branch on the infinite tree of reality. Of course, this theory remains just that, an interpretation of the quantum math that is as compelling as it is unproven. We have no technology to cross between these worlds, and no evidence that they truly exist beyond the equations. Yet it provides a breathtakingly vast canvas for possibility. If the many worlds interpretation is correct, then every potential past and every conceivable future is real, playing out somewhere in the sprawling multiverse. The question then shifts from whether we can change time to which version of time we wish to visit. But what if the universe itself refuses to allow a paradox? This is the elegant and somewhat chilling solution proposed by Russian physicist Igor Novikov. His self-consistency principle offers a very different answer to the grandfather paradox. Novikov asserted that the laws of physics simply do not permit contradictions. If time travel to the past is possible, then any actions a traveler takes there must have always been a part of the established timeline. You cannot change history because you have already done what you are going to do. Imagine you build a time machine and decide to journey back to prevent a famous tragedy. You arrive in the past, your plan clear in your mind, but as you raise your hand to intervene, something always happens to stop you. Perhaps a sudden crowd pushes you back, or a minor illness makes you too weak to act, or your own weapon simply jams at the critical moment. According to Novikov, these would not be mere coincidences. They would be the universe enforcing a kind of cosmic censorship, weaving a web of inevitable events to protect the consistency of cause and effect. Your attempt to change the past was always part of that past, and your failure was always the inevitable outcome. This makes time travel a profoundly passive experience. You could be a tourist in ancient Rome, but you could never save a single gladiator from his fate. You could witness the construction of the pyramids, but you could never leave a modern tool behind for the builders to find. Any action that would create a logical inconsistency is rendered impossible by a seemingly guided series of accidents and improbabilities. The timeline is a single, unbreakable thread, and the time traveler is just another fiber woven into its immutable fabric. This principle imposes a rigid order on the chaos of time travel, ensuring that every event, from the largest cosmic explosion to the smallest choice you make, fits together in a perfectly self-consistent whole. It is a universe that protects itself from the madness of paradox, but in doing so, it strips away our freedom to truly interact with the past. We are left as mere spectators on the river of time, allowed to watch the current flow, but forever forbidden from altering its course. Stephen Hawking proposed a cosmic rule that might forever lock the doors to the past. He called it the chronology protection conjecture, a principle stating that the laws of physics inherently prevent time travel on a large human scale. Hawking was not just being cautious, he was looking at the mathematics. He argued that if someone tried to create a closed time-like curve, perhaps using a wormhole or a warp drive, the universe would fight back. The moment such a time machine began to form, the vacuum of empty space around it would rebel. According to quantum theory, empty space is not truly empty. It is a seething foam of virtual particles, constantly flickering in and out of existence. These are particle and anti-particle pairs that borrow energy from the vacuum for an impossibly brief moment before annihilating each other. Normally, this quantum frenzy is balanced and invisible, but near a forming time machine, this balance would shatter. the looping path through time would allow these virtual particles to travel back to their own origin. A single particle could loop around again and again, gaining energy with each pass. This feedback loop would rapidly escalate, building an infinitely powerful surge of radiation that would obliterate the time machine before it could ever be used. It would be like a microphone feeding back in a deafening screech. Only this feedback would be a blast of raw energy capable of tearing apart the fabric of spacetime itself. This conjecture is not a proven law, but a compelling argument from one of history's greatest minds. It suggests the cosmos has a built-in immune system, one that attacks the paradox of time travel with overwhelming force. Yet the debate is far from settled. Some theoretical physicists argue there might be loopholes. Perhaps a sufficiently advanced civilization could find a way to stabilize the time machine against these quantum fluctuations. Or perhaps the infinite energy buildup only occurs in specific models that don't account for the full, unified theory of quantum gravity. This is the holy grail of modern physics, a theory that would finally marry Einstein's general relativity with the quantum world. It is possible that within this unknown framework, the rules are different. Maybe chronology protection is not an absolute law, but a barrier that could one day be engineered around. Hawking's conjecture does not kill the dream of time travel. Instead, it elevates the challenge, pushing it from the realm of mere engineering into the deepest mysteries of fundamental physics. To build a time machine, we may first need to learn how to negotiate with the universe itself. Another path to the past emerges from the equations of special relativity itself, written in the language of hypothetical particles called tachyons. These are not ordinary bits of matter, but theoretical entities defined by a single, extraordinary property. They must always travel faster than light. According to Einstein's own work, as an object approaches light speed, its mass effectively becomes infinite and its sense of time grinds to a halt. Tachyons, by their very definition, would live on the other side of this light speed barrier. For them, the cosmic rulebook would be flipped. From our perspective, a tachyon would not just be moving fast, it would be experiencing time in reverse. Imagine such a particle being emitted from a distant star and arriving at your detector tomorrow. From the tachyon's own point of view, it would be traveling backward through time, its journey beginning with your detection and ending at the star. This bizarre reversal opens a tantalizing possibility. If tachyons exist and we could learn to produce and control them, they might become the universe's ultimate messaging system. You could encode a signal onto a beam of tachyons and send it backward through time. A scientist in the present could, in theory, receive a warning about a future disaster, or an archaeologist could get answers directly from the ancient builders of a lost city. The tachyon would be a single-use time capsule carrying information from the future to a point in its own past. The obstacles to this dream, however, are monumental. First, no tachyon has ever been detected, and most physicists regard them as mathematical curiosities rather than real particles. The equations allow for them, but the universe shows no sign of actually using them. Even if they do exist, they are predicted to be incredibly unstable. A tachyon moving faster than light would likely lose energy rapidly, causing it to accelerate even more until it effectively vanishes from our reality. Attempting to slow one down or capture it would be like trying to catch a shadow in a net. The very act of interacting with it could destroy its delicate, time-reversed nature. Furthermore, using them for communication creates the same paradoxes we have encountered before. What happens if the message you receive tells you not to send the message in the first place? The universe seems to abhor such logical knots, and the tachyon's theoretical foundation offers no clear answer. So while this idea remains a fixture on the furthest fringe of physics, it serves as a powerful reminder that the seeds of time travel might be hidden not in massive cosmic structures, but in the ghostly, unseen particles that could be flashing through our laboratories at this very moment. The universe might not be a story unfolding moment by moment, but a completed book where every chapter exists at once. This is the block universe theory, a model where time is a dimension no different from length, width, or height. In this view, the past, present, and future are not successive states, but permanent coordinates in a vast four-dimensional structure. Your birth, your first steps, and every moment of your life are all equally real, fixed points in this cosmic block, just as Paris and Tokyo are fixed points on a map. Time travel within this framework is not about changing history, but simply about navigating to a different page in the book. A time machine would be less a magical device and more a vehicle that allows you to move along the time axis, the way a car moves you along a road. This elegant idea neatly sidesteps the terrifying paradoxes that plague other theories. If you traveled to the past, you would not be creating a new event. You would merely be occupying a location that has always contained your arrival. Your actions there were always a part of that moment, woven into the immutable fabric of the whole. The grandfather paradox simply cannot occur because the timeline is a single, unchangeable whole. Yet this profound solution comes with a staggering cost, the loss of our most fundamental experience. Our powerful, undeniable feeling of a flowing present, a moving now, is revealed as a grand illusion. Consciousness in this model is like a tiny spotlight moving slowly along the time axis, illuminating one frozen slice of reality after another, creating the subjective experience of a life unfolding. This raises a deeply unsettling question. If every moment is already written, do we truly have free will, or are we just reading a script written in the geometry of spacetime? The block universe offers a paradox-free path through time, but it asks us to surrender the very notion that we are the authors of our own story. A new phase of matter defies one of the most fundamental expectations of physics. Time crystals are not shimmering gems from a science fantasy novel. They are bizarre quantum systems that achieve a form of perpetual motion, not by moving through space but by oscillating in time. In a normal crystal, like a diamond, its atoms are arranged in a repeating pattern in space, locked in a rigid lattice. A time crystal's structure, however, repeats in time. Its atoms flip back and forth between two quantum states, ticking like a perfect, eternal clock. And this remarkable oscillation persists even in its ground state, the lowest possible energy level. This means the crystal ticks forever without consuming any energy, breaking what physicists call time translation symmetry. It is a system that is perpetually out of equilibrium, forever cycling without ever running down. The implications for time itself are staggering. If we can create and control these tiny quantum metronomes, could we scale them up into a new kind of technology for manipulating time? One speculative idea suggests that an unimaginably vast array of synchronized time crystals could be used to create a stable, repeating time loop. Picture a chamber whose walls are lined with trillions upon trillions of these perfect quantum clocks, all ticking in flawless unison. Their combined, rhythmic pulsation might impose a new kind of order on the space-time within the chamber, forcing it to resonate at a specific frequency. Anything or anyone inside might be caught in a temporal echo, experiencing the same few seconds or minutes over and over again. This would not be time travel in the classic sense, but a form of temporal stasis or a perfectly repeating pocket of reality. Another possibility is using such an array as an anchor, a fixed point in the flowing river of time. By creating a powerful, localized field of these oscillating systems, an advanced civilization might be able to decouple a small region of space from the external flow of time, effectively creating a room where time passes at a different rate. Step inside and you could watch the outside world speed up like a fast-forwarding video. Step outside and only a moment would have passed for you while years had flown by for everyone else. This offers a potential mechanism for controlled time manipulation that is rooted not in colossal gravity, but in the subtle, persistent ticking of the quantum world. We have already created primitive time crystals in laboratories, using chains of ions or dense clouds of atoms, proving the phenomenon is real. But harnessing them for temporal engineering would require a mastery of quantum physics far beyond our own. It would mean moving from controlling a few hundred atoms to orchestrating a cosmic symphony of them, a challenge that may take millennia to overcome. Yet the very existence of time crystals reveals a profound truth. Time may not be a featureless background. It could have a structure all its own, a texture that, with the right tools, we might one day learn to weave. 14. The ontological paradox asks if something can be born from nothing. This is the bootstrap paradox, a loop of existence with no beginning. Imagine a student of physics who one day receives a complex set of blueprints from an older, wiser version of themselves. The plans are for a time machine. The student spends their entire life studying these diagrams, perfecting the design, and finally, after decades of work, constructs the very device described. The first thing they do is travel back in time to find their younger self, and they hand over the blueprints that started it all, a simple, closed loop. But here is the devastating question: who actually designed the time machine? The information did not come from the student's mind, it was merely passed along. It did not emerge from the older self, for they only possessed it because they received it. The knowledge, the invention, exists in a perfect circle with no point of origin. It is an object or an idea that has simply always been, trapped in a cycle of its own making. This paradox attacks our deepest understanding of cause and effect. We are accustomed to a linear universe where everything has a creator, where every event is the result of a prior action. The bootstrap paradox shatters that linearity. It suggests that within a universe that permits time travel, certain elements might be self-creating, or perhaps more accurately, uncreated. They are just there, eternal passengers on a journey with no starting station. Think of a famous symphony composed by a musician who claims to have been inspired by a melody they heard in a dream. What if that dream was a faint echo from their future, a memory of themselves hearing the completed symphony from a time traveler? They write it down, it becomes a masterpiece, and centuries later, a fan uses a time machine to play a recording of it for the composer as a child. The music exists without a composer. It wrote itself. This is not just a puzzle for science fiction. Physicists and philosophers grapple with this because it reveals a terrifying possibility. If closed time-like curves are real, then our reality might be filled with these logical ghosts, ideas and objects that have no true author, no moment of invention. They simply are forever. The same strange rules that govern a single particle could forge a link across the ages. Quantum entanglement is a connection so profound that Einstein himself called it spooky action at a distance. It describes a pair of particles born together, their fates forever intertwined. Measure one particle here on Earth and find its spin is up, and its partner, even if it is on the other side of the galaxy, will instantly be found to have a spin down. This correlation happens faster than light, seemingly bypassing our conventional understanding of space and distance. It is as if the two particles are not two separate entities at all, but a single system existing in two places at once. This phenomenon of non-locality suggests that the universe possesses a hidden layer of connection, a web of relationships that operates outside the rules of our everyday reality. If this link can transcend space so effortlessly, could it also reach across time? Some theoretical physicists speculate that the strange logic of entanglement might not be bound by our arrow of time either. What if you could entangle two particles, then carefully send one of them on a journey through a time machine into the past? The instant you measure the particle you kept in the present, its entangled partner in the past would respond, creating an effect that ripples backward through history. In this speculative picture, the correlation would be established after one particle has traveled to the past, yet it would influence the state of that particle in the past. This would be a form of communication, not with radio waves, but with quantum states, where a decision made now echoes into what we perceive as yesterday. Taking this idea even further, what if we could scale this effect up from particles to people? Imagine a vast, complex system, a human-made object or even a living being that was perfectly entangled with another version of itself in the past. Manipulating the present system could, in theory, instantaneously alter its entangled twin in the past, effectively rewriting history through quantum correlation. It is a concept that turns causality on its head, suggesting that the future could reach back and shape the past. It is crucial to understand that this remains a fringe idea, a thought experiment that pushes the boundaries of quantum theory into realms it was never designed to describe. There is no experimental evidence for macroscopic entanglement across time, and most physicists would argue that the delicate state of entanglement would be instantly destroyed by the decoherence of any large, complex system. The universe seems to protect its deepest secrets with noise and instability. Yet, this speculative frontier highlights a breathtaking possibility. The same spooky link that binds two particles across a galaxy might be the very thread that could one day be woven into a tapestry connecting all of time. The universe appears perfectly balanced for our existence, a fact that has haunted cosmologists for decades. The force of gravity, the strength of the nuclear forces, the mass of fundamental particles, each of these constants is set to a value that seems almost magically precise. If any one of them were altered by even a tiny fraction, stars would not ignite, complex atoms would never form, and life as we know it would be impossible. This eerie fine-tuning is known as the anthropic principle, the observation that the universe we observe must be compatible with our existence as conscious observers. But what if this cosmic perfection is not a lucky accident, but the result of a deliberate act, a project of creation executed not at the beginning of time, but at its very end? Consider a civilization in the far, far future, a society that has mastered not only time travel but the fundamental engineering of reality itself. These beings, who might be our own descendants transformed beyond recognition, look back across the eons and realize their universe is aging, cooling, and dying. To ensure their own lineage survives, they decide to enact the ultimate act of cosmic preservation. Using technology we cannot even conceive of, they reach backward through time to the moment of the Big Bang itself. They fine-tune the initial conditions, adjusting the dials on the universe's birth with unimaginable precision, setting the constants exactly as they need to be to guarantee that stars, planets, and eventually intelligent life will arise. In this breathtaking loop of causality, these future engineers are responsible for creating the very universe that allows them to evolve and develop time travel in the first place. They are the authors of their own origin story, planting the seed that will grow into the tree from which they were born. This transforms the anthropic principle from a passive observation into an active, self-fulfilling prophecy. The fine-tuning is not a mystery, it is a signature, a message from the future written into the fabric of the cosmos itself. This idea creates a bootstrap paradox of unparalleled scale. Who created the universe? The future time travelers did, but who created the time travelers? The universe did. It is a perfect, closed circle of existence with no ultimate beginning, a cosmic Ouroboros, the snake eating its own tail. The universe exists simply because it has always existed in this self-consistent loop, a timeless engine of its own creation. While this remains a highly speculative thought experiment, it offers a profound and poetic resolution to one of science's greatest puzzles. It suggests that the answer to why we are here might not lie in a divine creator or random chance, but in our own distant future, where our descendants complete the circle of time by ensuring their own past. 17 brings us to a universe spinning as a whole. The brilliant logician Kurt Gödel found a solution to Einstein's own equations that described a cosmos in relentless rotation. In this model, every galaxy, every star, every particle is swept along in a vast cosmic whirlpool. This universal spin does not just move matter, it twists the fabric of spacetime itself into a series of endless looping paths known as closed timelike curves. The consequence is staggering. You could simply board a spacecraft and embark on a long journey, flying a wide enough arc through this revolving cosmos. If you traveled far enough, you would not arrive at a new destination in space, but at your very own launch date. You would return to the moment you left, having completed a circuit not around a star but around time itself. There would be no need for black holes or wormholes. The entire universe would be your time machine, yet observations of our own cosmos reveal a starkly different reality. We look out at the distant galaxies and the faint echo of the Big Bang, and we find no evidence of such an overall rotation. The universe expands, but it does not appear to spin on that all-encompassing scale. This places Gödel's brilliant mathematical discovery in the realm of a fascinating thought experiment, a proof of concept written in the language of general relativity. It demonstrates with absolute clarity that the laws of physics, as described by Einstein, contain no rule that outright bans travel into the past. The universe could have been constructed this way, and in that alternate reality, time travel would be a simple fact of navigation. Our reality just chose a different set of initial conditions, so while we may not live in Gödel's spinning universe, its existence in the equations is a profound message. It tells us that the barrier to time travel is not a fundamental law written in stone, but perhaps just an accident of our cosmic birth. Our reality might be a magnificent illusion, a cosmic sleight of hand. The holographic principle proposes that the universe we experience, with its 3 dimensions of space and 1 of time, is actually a holographic projection. All the information contained within any volume of space, every star, every planet, every one of your memories, could be perfectly encoded on its 2-dimensional boundary, like a movie being projected from the surface of a screen. This is not a metaphor. The mathematics comes directly from the study of black holes, where physicists found that the maximum amount of information a black hole can contain is not proportional to its volume, but to the area of its event horizon. It is as if the entire interior of a black hole is painted onto its surface. If this is true for the most extreme objects in the cosmos, why not for the entire universe? We could be living inside a hologram with the cosmic microwave background, the afterglow of the Big Bang, acting as the potential projection surface for all of reality. This idea completely rewrites our understanding of time. The past is not gone and the future is not unformed. They are simply different sets of data written on this cosmic hard drive. Time, in this view, is not a flowing river but a static library. Your entire life, from birth to death, is a permanent entry in the universal catalogue. Time travel, then, would not require a ship or a wormhole. It would be a feat of information technology. An advanced civilization that learned to read and manipulate the cosmic hologram could, in theory, scroll backward through the data to retrieve any moment from the past. They would not be visiting the past so much as they would be accessing a perfect recording of it. A recording so flawless it is indistinguishable from reality itself. The next step is even more profound. If you can read the data, could you rewrite it? Could you alter the holographic code to change a past event? This would be the ultimate form of time travel, not as a journey, but as an act of cosmic editing. You would not be stepping into a time machine. You would be sitting at a console and reprogramming history. The paradoxes this creates are dizzying. If you erased a war from the historical record, would every memory of that conflict simply vanish from the collective consciousness? Would the new, peaceful timeline instantly become the only reality that ever was? The holographic principle suggests that our experience of cause and effect, of a linear and unchangeable past, might be a necessary feature of the projection, a way for our limited consciousness to make sense of the vast encoded data. To change the data would be to break the projector, potentially unraveling the consistency of the entire simulation. This idea pushes time travel from the realm of physics into the domain of information science, asking us whether the universe is ultimately made of atoms or of bits. Rotation itself can carve a path through time, even in the simplest of substances. Consider a cloud of dust, fine particles all spinning together in perfect unison around a central axis. This is the essence of the Van Stockham dust solution, a remarkably clean answer to Einstein's complex equations of gravity. The model describes an infinitely long cylinder composed of nothing but this rigidly rotating dust, a cosmic vortex of fine powder whirling through the void. There are no complex forces holding it together, no solid structure, just the delicate balance of gravity and centrifugal force. Yet, this seemingly simple setup produces an effect of profound consequence. The immense mass and rapid spin of this dust cylinder create a powerful frame-dragging effect, a phenomenon where the rotating matter literally grabs the fabric of space-time and twists it along for the ride. The faster the dust spins, the more it contorts the coordinates of reality around it, warping them into a tight helix. If you were to pilot a ship on a very specific spiral path around this whirling cloud, you could find yourself on a closed timelike curve. Your journey through space would become a loop that circles back to your own past, allowing you to arrive at a moment before you ever began your voyage. It is a time machine built from nothing but motion and dust. The elegance of this model lies in its mathematical purity. Unlike the complex physics of a wormhole or a black hole, the Van Stockham solution provides a clear and exact demonstration within general relativity, showing unequivocally how mere matter in motion can twist the flow of time into a knot. But this beautiful simplicity comes with impossible requirements. For the closed time-like curves to appear, the cylinder must be infinitely long, a physical object stretching forever in both directions, which is a concept our finite universe simply cannot accommodate. Furthermore, the dust cloud itself is inherently unstable. Any slight perturbation, a passing gravitational wave or the gravitational pull of a single star would cause the delicate balance to collapse. The cloud would either fly apart or collapse inward under its own gravity, instantly destroying the fragile time loop. So while Van Stockham dust stands as a brilliant mathematical proof that rotation can be a direct engine for time travel, it remains a blueprint that reality seems to forbid. It shows us the power hidden within a spinning cosmos, a power we can write down with perfect clarity, but may never be able to hold in our hands. A wormhole becomes a true time machine through the simple, relentless ticking of clocks. To transform this cosmic bridge from a spatial shortcut into a gateway to the past, you only need to create a difference in the flow of time between its two mouths. One method is to take one mouth of the wormhole and place it deep within an intense gravitational field, perhaps by hovering it just outside the event horizon of a black hole. There, where gravity is overwhelming, time would crawl. The other mouth remains in a region of weak gravity, where time flows at its normal, familiar rate. Leave them in this configuration for a while. Years could pass for the stationary mouth, while only days or hours pass for the mouth bathed in crushing gravity. Now a traveler steps into the mouth that has experienced less time, the one that has aged more slowly. They pass through the tunnel and emerge from the other side. But they do not just arrive in another location, they arrive at a moment in time that corresponds to the slower-aged mouth's personal history. They exit into the past relative to when they entered. If the time difference between the mouths was 5 years, the traveler would emerge 5 years before the date they began their journey. The same effect could be achieved without immense gravity, by instead moving one mouth of the wormhole at a significant fraction of light speed. The relativistic effects of high velocity would cause that mouth to age slower than its stationary twin, creating the same essential time differential. The traveler always enters the mouth that is younger in terms of external time, and exits into the past through the mouth that is older. This is not magic, it is a direct consequence of the time dilation we know to be real. The monumental challenge, of course, lies in the wormhole itself. Keeping it stable against its own gravitational tendency to collapse requires a scaffolding of exotic matter with negative energy, a substance we have yet to find or create in any usable quantity. But even if we solved that, another terrifying phenomenon awaits. As a traveler moves through the wormhole toward the past, they would encounter what is known as a Cauchy horizon, a boundary beyond which predictability breaks down. At this threshold, any light or radiation accompanying the traveler would be compressed into an infinitely energetic, infinitely blue-shifted wall. Each photon would be boosted to such a high frequency that it would carry the destructive power of a cosmic ray. This sudden, catastrophic surge of energy would likely vaporize the traveler and destroy the wormhole tunnel in an instant, a feedback loop of radiation ensuring the past remains protected. This blue shift problem is a formidable guardian of chronology, suggesting that while the mathematics of differential aging is sound, the universe might deploy ultimate fail-safes to keep its timeline clean. Deep beneath the smooth, continuous reality we perceive, the universe may be a seething, chaotic ocean. This is the domain of quantum gravity, a theoretical frontier where the rules of Einstein's smooth spacetime break down and are replaced by something far wilder. At the tiniest imaginable scales, the Planck length, the very fabric of reality might not be a fabric at all. Instead, it could be a frothing, turbulent foam. This spacetime foam is a quantum frenzy where tiny wormholes and microscopic black holes constantly bubble into existence, only to vanish a fraction of a second later. It is a foam of reality itself, where the concepts of here and there, before and after, lose all meaning. The ground beneath your feet, the air you breathe, all of it could be resting upon this quantum storm. This leads to a staggering proposition. What if the universe is already filled with natural time tunnels? Not the grand, stable wormholes of theory, but countless fleeting gateways, each one a potential doorway to another when. The challenge would not be to build a time machine from scratch, but to find a way to catch one of these quantum bubbles and hold it open. Imagine a technology so advanced it could reach into this foam, identify a nascent wormhole, and inject it with a form of exotic energy. This energy would act as a scaffold, preventing the tiny tunnel from collapsing and allowing it to be gently expanded, like blowing a cosmic soap bubble. A civilization that mastered this could, in theory, pluck a ready-made time gateway from the quantum vacuum, stabilizing what nature creates only for an instant. The implications are profound. If space-time foam is real, then the raw materials for time travel are everywhere, woven into the empty space between atoms. The key to unlocking the ages would not be found in the gravity of a black hole or the spin of a cosmic cylinder, but in the humming, invisible quantum noise that underlies everything. It would mean that time travel is not an engineering project on a cosmic scale, but a feat of ultra-fine control, a mastery of the very texture of reality. Of course, this remains one of the most speculative ideas in all of physics. We lack a complete theory of quantum gravity, and the energy scales required to manipulate space-time foam are far beyond our reach. Yet, it offers a beautiful and humbling vision. The path to other times might not be a highway we must construct, but a hidden network of footpaths already there, waiting for us to learn how to see them. This philosophical stance is known as eternalism, a perspective that treats time as a dimension where every moment is a fixed and permanent coordinate. It stands in stark contrast to presentism, the intuitive belief that only the current moment is real, while the past has vanished and the future is not yet formed. Eternalism argues that your fifth birthday is just as real as the moment you are experiencing right now. They simply exist at different addresses in the vast four-dimensional structure of spacetime. Within this framework, the idea of time travel undergoes a radical simplification. journeying to the past is not about rewriting history or altering a fragile timeline. It is merely a form of navigation, moving from your current temporal location to another, pre-existing one, much like traveling from New York to Paris. The past you wish to visit is not a ghostly memory, but a fully realized place, complete and unchangeable. This has profound implications for what it would mean to encounter your own past self. According to eternalism, you would not be meeting a fragile echo or a version of yourself that is any less real. You would be interacting with another individual who exists at a different point in the space-time manifold. Both of you are equally valid, permanent parts of the cosmic whole. This person shares your memories up to that point in their personal timeline, but from the moment of your arrival, your experiences begin to diverge. They continue living toward the future that you remember, while you, the traveler, are now a visitor from what is to them a time that has not yet happened. Your memories are not a paradox, but a record of a longer journey through the block universe. This view neatly dissolves many of the terrifying logical knots of time travel, but it introduces a deeply personal puzzle about identity. If both versions of you are real, which one is the true you? The answer from eternalism is that they both are. You are not a single point of consciousness, but a sprawling, four-dimensional worm woven through space-time from birth to death. Every laugh, every tear, every choice is a permanent part of this extended structure. Meeting your younger self would be an encounter between two different temporal segments of the same continuous object. This challenges our most fundamental experience of a single, flowing life, suggesting that our sense of a unified self may be an illusion crafted by a consciousness that can only perceive one slice of reality at a time. The eternalist universe is a frozen, magnificent sculpture, and we are simply tracing its contours, mistaking our slow progress for the act of creation. Exotic matter is the key that could unlock nearly every theoretical time machine we have discussed, yet it is a key made of pure paradox. This is not just an undiscovered element on the periodic table. Exotic matter is defined by a property that seems to defy the very nature of reality, a negative energy density. While normal matter and energy create a positive curvature in space-time, manifesting as the attractive force of gravity, exotic matter would do the opposite. It would generate a kind of repulsive gravity, pushing space-time apart rather than pulling it together. This bizarre characteristic is not merely a curious footnote. It is the fundamental engineering requirement for the two most famous blueprints for time travel. First, consider the wormhole. A naturally occurring tunnel through space-time would be incredibly unstable, collapsing into a singularity in an instant under the immense pressure of its own gravitational field. To prop this cosmic shortcut open, to make it traversable for a ship or even a person, you would need to line its throat with a stable shell of this exotic matter. It would act as a permanent scaffold, an anti-gravitational force counteracting the natural tendency of the tunnel to pinch shut. Without it, your gateway to the stars would snap closed faster than you could enter. The same impossible fuel is required for the Alcubierre warp drive, to contract space-time in front of the ship and expand it behind, creating the moving wave that carries you faster than light. You need a stable ring of exotic matter surrounding the warp bubble. This ring generates the precise warping needed to surf the fabric of the cosmos. In both cases, the exotic matter is not an optional component, it is the very heart of the machine. So where could we possibly find such a substance? We have actually glimpsed its shadowy effects in laboratory experiments. The Casimir effect demonstrates this principle on a tiny scale. When you place two perfectly smooth, uncharged metal plates extremely close together in a vacuum, they experience a faint but measurable force pushing them together. Why? Because the space between the plates is so confined that it excludes some of the longer wavelengths of virtual particles that constantly flicker in and out of existence in the quantum foam. The space outside the plate still has this full, seething energy, creating a pressure differential. From a certain perspective, the region between the plates can be said to have a lower energy density than the surrounding vacuum, effectively manifesting a form of negative energy. This is a real, measured quantum phenomenon, but the scale of the requirement is where the dream collides with physical reality. The amount of negative energy needed to stabilize a wormhole large enough for a person is staggering. Conservative estimates suggest you would need to convert the equivalent mass of Jupiter into this exotic form. For an Alcubierre drive capable of moving a modest spacecraft, the energy requirement might be greater than the total mass energy of the entire observable universe. This is not an engineering challenge, it is a fundamental barrier that redefines the word impossible. It means that while the mathematics of general relativity generously allows for these fantastic machines, the universe's own quantum rulebook seems to demand a price too high for any civilization to pay. The search for exotic matter is therefore more than a quest for a new material. It is a direct confrontation with the deepest laws of physics, a test to see if the cosmos will ever permit us to become the masters of time. A particle can sometimes vanish from one side of an impenetrable wall and instantly reappear on the other. This is quantum tunneling, a bizarre but proven phenomenon where the rules of classical physics break down. In the subatomic world, particles are not tiny billiard balls but clouds of probability. There is a faint but real chance that an electron can simply find itself on the wrong side of a barrier, as if it momentarily borrowed the energy to phase through an otherwise solid wall. Now stretch this concept to its absolute limit. What if the barrier is not a wall of energy but the fabric of time itself? Could an entire object, or even a person, quantum tunnel from one moment to another, effectively phasing out of the present and reappearing in the past or future? This would not be a journey through a wormhole or a ride on a warp bubble. It would be a discontinuous leap, a blink of an eye transition from one temporal address to another. The object would not move through the intervening time. It would simply cease to exist in one era and pop into existence in another. The probability of such an event for anything larger than a single atom is so infinitesimally small that it borders on the impossible. For a single electron to tunnel through a thin barrier is a rare event. For all the trillions upon trillions of atoms in a human body to simultaneously tunnel through the monumental barrier of spacetime is a number so small it has no practical meaning. It is akin to a tornado sweeping through a junkyard and spontaneously assembling a fully functional jet airliner, not once but trillions of times in a row. So how could we ever hope to harness such an elusive effect? The answer might lie in forcing these trillions of atoms to act as one. In a normal object, every particle behaves independently, a chaotic democracy of motion. But if we could place an object into a state of perfect quantum coherence, where every single atom is entangled with every other, the entire system would behave as a single macroscopic quantum entity. In this unified state, the probability of tunneling would no longer be calculated atom by atom, but for the object as a whole. It would be one single collective roll of the dice, a unified leap through time. We have already achieved this kind of coherence on a small scale, with clouds of ultra-cold atoms behaving as a single superatom, or Bose-Einstein condensate. Scaling this up to a complex, living organism is a challenge that may never be overcome, as maintaining such a fragile quantum state requires perfect isolation from the slightest interference. The warmth of a single photon or the vibration of a single molecule would shatter the coherence, collapsing the possibility in an instant. Yet, this idea pushes the very definition of time travel. It suggests a method that bypasses gravity and general relativity entirely, relying solely on the ghostly rules of the quantum realm. It is a leap of faith written in the language of probability, a reminder that on the most fundamental level, our existence in this very moment is merely the outcome of a dice roll that has for now landed in our favor. The ultimate fate of the cosmos could be the very engine that powers time travel. Dark energy, the mysterious force accelerating the expansion of our universe, is not just pushing galaxies apart. It might be fundamentally reshaping the topology of spacetime itself, creating structures where the normal rules of cause and effect no longer apply. As dark energy continues its work over trillions of years, the universe will become a colder, lonelier place. Galaxies beyond our local group will fade from view, their light unable to overcome the ever-increasing expansion of space. In this distant epoch, the cosmos will be dominated by vast, nearly empty voids, punctuated by isolated galactic clusters that have become causally disconnected from one another. Each of these isolated regions could become its own island universe, a self-contained bubble of reality with its own unique space-time geometry. Within one of these island universes, the relentless pull of dark energy might create conditions ripe for closed timelike curves. The intense, repulsive gravity of dark energy could, in theory, stabilize bizarre space-time structures that are impossible in our current cosmic era. Imagine a civilization surviving in one of these far-future bubbles. They would look out into a void, seeing only the dim stars of their own cluster, the rest of the cosmos forever lost to them. But with nothing else to conquer, they might turn their ultimate knowledge inward to the manipulation of spacetime itself. Using the unique geometry of their dark energy-dominated bubble, they could theoretically engineer a region where spacetime folds back on itself. A ship could travel in what seems like a straight line, only to return to its own past, trapped in a time loop within the confines of their island home. This would not be time travel as a means of exploring history, but as a consequence of a dying universe's final architecture. The cosmic acceleration that dooms the universe to isolation might paradoxically be the very thing that makes time loops a physical possibility. It is a haunting thought that the key to traversing time may only manifest when the universe is at its most empty and desolate, a final gift from the fading cosmos to whatever intelligence remains. The grandfather paradox remains the ultimate test for any theory of time travel. It asks a brutally simple question: what if you journey to the past and prevent your own grandfather from meeting your grandmother? You would ensure your own birth never happens, which means you could never have traveled back to stop it in the first place. This logical knot seems to unravel the very possibility of moving through time, creating a contradiction that the universe should not allow. Yet physicists and philosophers have proposed several compelling ways this paradox could be resolved, each one reshaping our understanding of reality. The first solution is one of cosmic censorship, embodied by the Novikov self-consistency principle. This idea asserts the laws of physics simply forbid paradoxes. If you travel back with the intent to kill your grandfather, you will inevitably fail. Your gun will jam at the critical moment, a sudden distraction will pull you away, or a previously unknown heart condition will strike him down just before you act. These are not random accidents, but the universe enforcing a kind of predetermined harmony. Your attempt was always part of the timeline, and your failure was the inevitable outcome. In this view, free will is an illusion when it comes to altering the established past. You are merely an actor playing a role that was written long before you arrived on the stage. A second, and far more expansive, answer comes from the many worlds interpretation of quantum mechanics. Under this model, your violent act does not change your own history. Instead, the moment you interfere, the timeline splits. You create a new, parallel branch of reality where your grandfather dies young and you are never born. Your original timeline, with your original history and your living grandparents, continues on completely unaffected. You become a permanent resident of the new reality you created, a branch with its own future that no longer includes you. This resolution preserves free will at a colossal cost, multiplying the cosmos into a near-infinite tapestry of alternate histories. Every choice, every chance event spawns a new universe, and the time traveler is simply a catalyst for a branching process that was already happening at every moment. The final resolution is the most philosophically stark, the concept of a single, unchangeable timeline. In this block universe, the past is a fixed and permanent place. If you travel to the past, then you have always been a part of that past. Your arrival and your actions were woven into the fabric of history from the very beginning. Perhaps you were the mysterious stranger your family stories always mentioned, the one who indirectly caused your grandparents to meet. The question of killing your grandfather is moot because you did not and you never could have. Your journey did not change history, it completed it. This view offers perfect consistency but demands we surrender any notion of altering the past. We are not authors of our destiny, but readers discovering a story that has already been fully written. The grandfather paradox is far more than a puzzle for science fiction. It forces us to confront the deepest questions about cause and effect, and whether the universe is a single, rigid narrative or a boundless collection of possibilities waiting to be realized. Some of the most profound questions in mathematics and physics are not just difficult, they are formally uncomputable. There are problems that, by their very nature, no finite computer, no matter how powerful, could ever solve in a finite amount of time. Their solutions require an infinite number of computational steps. Yet, what if you could cheat time itself to get the answer? This is the promise held within Malamute-Hogarth spacetimes. These are not machines, but entire cosmic environments, specific solutions to Einstein's equations of general relativity, where the normal relationship between time and accomplishment is broken. In a Malamute-Hogarth universe, two different observers can experience time in two radically different ways. One observer could embark on a finite journey, lasting perhaps just a few years of their own life. Meanwhile, a second observer, or even a computer, left behind in a different part of this warped spacetime, could experience an infinite amount of time, completing a task that requires an endless number of steps. The first traveler would then return to collect the answer to a problem that should have been forever out of reach. Imagine a computer programmed to search for the ultimate secret of prime numbers or to prove the consistency of all mathematics. In our normal world, such a machine would run forever, its fans humming until the end of time. But in a Malamute-Hogarth spacetime, you could leave it running in a region where time is infinitely stretched, go off on a brief expedition, and come back to find its work complete. The answer would be waiting for you, the result of an infinite computation witnessed in your finite lifetime. This incredible feat demands an equally incredible cosmic structure. The most likely way to create such a spacetime is through a naked singularity, a gravitational pit of infinite density without an event horizon to shield it from the rest of the universe. Unlike the black holes we are familiar with, a naked singularity's bizarre physics would be exposed for all to see, potentially creating the extreme temporal distortions needed. An observer could carefully orbit this singularity, their personal clock ticking away a few minutes, while watching an infinite future unfold in the universe around them. This idea links the physics of time travel directly to the philosophy of knowledge. It suggests that the absolute limits of what can be known, the boundaries of mathematics and computation, might not be fixed. They could depend entirely on the structure of the cosmos you inhabit. A civilization born into a Malamute-Hogarth universe would have access to truths that are forever hidden from us, not because they are smarter, but because their reality is fundamentally more accommodating to infinite inquiry. They could solve the unsolvable not with better brains, but by using time itself as a tool. Physics demands predictability from the cosmos. For the universe to make any sense at all, the present must logically determine the future. This fundamental requirement is known as the Cauchy problem in general relativity. It asks a simple but profound question. If you know everything about the universe at one single moment, can you calculate its entire future? For this to be possible, spacetime must possess a special property called global hyperbolicity. Think of a globally hyperbolic universe as having a single, universal now, a moment that acts as a clean starting line. This is the Cauchy surface, a three-dimensional slice of spacetime where you could theoretically write down the position and momentum of every particle, every ripple of gravity, every quantum field. From this complete snapshot, the laws of physics would then unfurl the future in a deterministic, predictable way. It is the cosmic equivalent of knowing every piece on a chessboard and being able to calculate the entire game from that point forward. This is the orderly, classical universe that Einstein envisioned, a reality where cause and effect are sacred and the future is, in principle, knowable. Now introduce a single closed timelike curve into this picture. The moment a path loops back from the future to the past, the entire elegant structure collapses. The clean starting line of the Cauchy surface is shattered. How can you possibly set initial conditions for the future when information from that future can come back and interfere with the past? The causal sequence becomes a tangled mess, a knot of influences with no clear beginning. The future is no longer determined solely by the past because the future is now meddling with the past. Imagine trying to solve a complex equation, but the answer keeps changing the question you started with. The result is not a prediction but a paradox. This violation of global hyperbolicity is why many physicists argue that time travel must be forbidden by the deeper laws of nature. They see the breakdown of predictability not as a thrilling possibility, but as a fatal flaw in any theory that permits journeys to the past. The universe, in their view, must protect its own logical consistency at all costs. Yet, a different perspective sees this not as a prohibition but as a signpost. The violent failure of global hyperbolicity in the presence of closed timelike curves might be screaming that Einstein's theory of gravity is incomplete. General relativity is a masterpiece, but it is a classical theory that does not account for the fuzzy, probabilistic rules of the quantum world. The seething chaos of quantum gravity, which governs the universe at its very smallest scales, might be able to handle these causal loops in a way that our current physics cannot. Perhaps in a full theory of quantum gravity, the paradoxes smooth out. Maybe the future influencing the past is not a logical dead end, but a complex feedback loop that a more advanced physics can resolve without contradiction. The debate is far from settled. It pits a desire for a predictable, classical cosmos against the tantalizing possibility that reality is far stranger and more interconnected than we ever dreamed. The fate of time travel may ultimately depend on whether the universe values neat equations over boundless causal wonder. Our journey through the cosmos now takes us to the very smallest scales of reality, where the fabric of spacetime itself may be woven from unimaginably tiny, vibrating strings. This is string theory, a leading candidate for the long-sought theory of everything, and it paints a picture of the universe with far more dimensions than the four we experience. In this framework, our entire universe might be a three-dimensional brain, a sort of cosmic membrane floating within a much larger, higher-dimensional realm known as the bulk. Think of our reality as a single, impossibly thin slice of bread adrift in a vast, multidimensional loaf. The existence of other brains, other slices parallel to our own, is a natural consequence of this model. And it is in the collisions and gentle interactions between these neighboring brains that a new kind of time travel might become possible. When two of these multidimensional worlds brush against each other in the bulk, the energy released could be staggering. Such a cosmic event might not just create a new universe, it could momentarily tear the fabric of both brains, stitching them together with a temporary wormhole. This would not be a tunnel carved through our familiar space, but a bridge that arcs through the higher dimensions of the bulk, connecting 2 points in time as easily as it connects 2 points in space. The complex, folded topology of these extra dimensions provides a rich landscape for such structures to form naturally. A wormhole generated by a brain collision could have its two mouths anchored at different moments in time, turning it into a ready-made time gateway. The very geometry of the higher dimensional space could force a causal loop, where the future of one brain becomes the past of another. For a civilization that learned to navigate the bulk or to induce controlled brain interactions, time travel could become less about engineering a machine and more about charting a course through a multidimensional ocean. Yet, this breathtaking vision remains shrouded in profound uncertainty. String theory is a mathematical masterpiece, but it is not yet a complete physical theory. It has not produced definitive, testable predictions about time machines or brain collisions. The energy scales required to probe these extra dimensions or to witness brain dynamics are far beyond the reach of any particle accelerator we could ever build. We are like flatlanders trying to comprehend a cube, our tools and senses limited to a narrow slice of a much grander reality. The promise, however, is immense. If string theory is correct, then the universe is not just stranger than we imagine, it is stranger than we can imagine. The raw materials for time travel may be all around us, woven into the hidden, curled-up dimensions that define the very essence of existence, waiting for a future physics to reveal their secrets. The final theory brings our journey inward to the very nature of our own minds. We have explored cosmic strings and quantum foam, but the most intimate barrier to time travel might be the one inside our heads. Our perception of time, the psychological arrow, flows unshakably forward. This is not an accident of consciousness, but is deeply entangled with the physical world. The universe itself possesses a thermodynamic arrow of time, a direction defined by increasing disorder, where ice melts in a glass and never spontaneously refreezes. Our brains are biological engines that have evolved within this stream of increasing entropy. Our memories are formed, they accumulate, and they create the unshakable narrative of a life moving from birth to death. This forward march is so fundamental to our cognition that reversing it could be mentally catastrophic. Imagine stepping out of a time machine into a world where cause and effect are inverted. You would see smoke gather into a cigarette, water in a puddle leap up to form a cloud, and people walking backward, their words a garbled reverse echo before they form a thought. Your brain, wired for a universe of increasing disorder, would desperately try to impose its own narrative on this chaos, likely resulting in a profound and paralyzing cognitive dissonance. The sheer sensory overload could trigger psychosis, as the mind's fundamental operating system confronts a reality for which it has no programming. This suggests that building the machine is only half the battle. A successful journey through time might require a way to reorient the traveler's own psychological arrow. Perhaps advanced neurotechnology could temporarily rewire the brain's perception, filtering sensory input to create a coherent, albeit reversed, experience of events. Alternatively, travelers might need to be placed in a state of suspended animation or hibernation for the journey itself, their consciousness dormant until they arrive safely in the past or future, thus avoiding the mental whiplash of moving against the temporal current. This final theory humbles our grandest ambitions. It posits that to truly master time, we must first master the mind. The ultimate time machine may need two keys, one forged from the laws of physics, and the other from a deep understanding of consciousness itself. Perhaps our reality is not a cosmic accident, but an intricate digital creation. The simulation hypothesis proposes that everything we know, from the farthest galaxy to the feeling of your own heartbeat, is the product of an unfathomably advanced computer program. If this is true, then time travel loses its mystery and becomes a matter of data management. The past is not a lost country, but a saved file. The future is not unwritten, but a set of potential states yet to be rendered. To journey through time, you would not need a wormhole or a warp drive. You would simply need administrative access to the simulation's core code. You could load a previous save point, effectively reverting the entire universe to a prior moment. This would resolve every paradox with the cold logic of a programmer. If you tried to create a grandfather paradox, the system could simply crash, or more likely, it would enforce a rule set that prevents any action from altering your own personal data stream. ensuring you could observe the past but never fundamentally change the events that led to your own login into the system. Your presence in the past would be a read-only experience, a temporary overlay that cannot overwrite the established code. This framework bypasses the immense complexities of general relativity and quantum mechanics entirely. There is no need for exotic matter or cosmic strings when time travel is just a feature of the operating system. The thermodynamic arrow of time, the one that makes ice melt and memories form, could be a simple variable set by the architects to give the simulation a coherent narrative flow. The strange results of quantum mechanics, like particles being in two places at once, might just be the result of processing shortcuts or lazy loading of assets in the cosmic codebase. While this idea is deeply metaphysical and currently untestable, it offers a startlingly clean explanation. It turns the grand philosophical questions of free will and destiny into questions of user permissions and sandbox modes. Are we players with agency or non-player characters following a script? The simulation hypothesis does not so much solve the puzzle of time travel as it does recast the entire universe in a light where the puzzle never truly existed in the first place. The greatest journey through time might not be a physical voyage, but a command line instruction waiting to be discovered. We have journeyed through 30 distinct visions of time, from the solid bedrock of Einstein's relativity to the wild frontiers of quantum foam and simulated realities. Though a working time machine remains a dream of science fiction, this exploration reveals a profound truth: the laws of physics do not slam the door shut. They leave it tantalizingly ajar, inviting us to push further. This pursuit is far more than an engineering challenge. It is a journey that stretches the very limits of science, forcing us to confront the deepest questions about the nature of reality itself. What is cause and effect? Do we live in a single unchangeable timeline or a multiverse of infinite possibilities? And what does our place in this cosmic puzzle truly mean? The search for answers reshapes our understanding of the universe and our role within it. We want to hear your thoughts. Which of these 30 theories do you find most compelling? The elegant loop of the wormhole, the infinite branches of the many worlds, or the cosmic code of the simulation hypothesis? Let us know in the comments below, and if you enjoyed this journey to the edge of physics, be sure to subscribe for more adventures into the great mysteries of the cosmos.